We have two things to do today. Where we left off yesterday class was 1 millimeter, 1 angstrom away from capacitors and capacitance. And we talked a lot about capacitors, but I did not yet quite define capacitance. We're going to fix that, and I want to spend most of the class doing a practical example of a capacitor and then using that as a test bed, toolbox, using that as an example to practice proportional reasoning and logical thinking about quantities. Then the second thing is briefly before we go, I'm going to do one more homework problem for you. The voltage of multiple charges is so simple, so easy, so quick, and let's do that first. Let's do that first because it's so fast. There is one additional formula for point charge voltages that I have not given you. And I want to emphasize, by the way, before I show it to you, that this is correct. No, I did not make a mistake, other than not fitting this in that lecture more betterly. It looks just like, but with a slight change, the electric field formula. Yes, that's true. There's a reason why I encourage all y'all to memorize the core equations as fast as you can, because we want to be able to notice these patterns. Okay. Here, first off, here is the voltage of 1 point charge and distance r away. It's exactly like the electric field, but not squared. The voltage at distance r meters away from a source charge big Q is kq on r. K is the same constant as before. That's it. Now let's do an example and plug in numbers and do this. Last week, I emphasized, I gave a pro tip that is always use positive source charge and reason using logic about whether field goes this way, that way, or the other way. Delma, yes, there are no circles. I mean, there could be a circle, but there's not in this case. So I encouraged you always use positive Q. You're welcome. Always use positive source charge and then think logically about, well, is positive charge being pushed this way, that way, or the other way? That's the direction of the electric field. Voltage is just a number. It has no direction. And I have not seen students screw up signs if you just plug in plus or minus charge. So you can use negative source charge here, and you are very likely to get the right number. As I said a moment ago, when you have more than one source charge, you just add them up. You add up the voltage due to A, the voltage due to B, voltage due to C. It's, as I said, it's that simple. It's very simple idea. Electric field in 2 dimensions uses trigonometry that's beyond the scope of how I'm teaching this year. So we're not going to do electric field in multiple dimensions, but voltage, easy peasy, lemon squeezy. Do this. And I need to change the letters. I challenge you to find the individual contributions, A, B, C, and D. We've got a rectangle of charges. My test charge with a test charge of -2 coulombs is down here. And I've got sources of 6, 7, and -4 at the corners of a 3x4 rectangle. Give her a shot. Ready, set, go. $9 billion, just like before. Dalma, identify what charge is A. Look at where A is relative to where you're asked about. I'm asking to find the voltage of each of these charges at location at the lower left corner. So if you want to find the voltage from A, use where is A relative to that. If you want to find the voltage due to B, you use where is B relative to that test point. If you want to find the voltage from C, use the distance to the test point from C. Good. Yes. The formula that I didn't somehow. We're talking about some charges. Voltage here point charge, KT divided by R. Then we're applying it. I've got three source charges, A, B, and C. And find the voltage of this position of the test unit. Hmm? Who's stuck? You're all working productively? All interpreting? Want me to do A? Oh, okay. Correct. Yeah, good job. So, is within two across S challenge. I should be very precise. It would be voltage relative to a point very far away. Voltage relative to voltage is in places. So really use it as the value of voltage. There's no for now. Maybe no results. Around the HR, there is a voltage existing in free space. The reference point is the phone. It's a voltage. Very different than the far away. Again, this one that's very far away. So that's where we're flying. We'll look at what kind of there are. Yeah. Sure. Yay, many correct answers. Okay, I'm gonna start there are some wrong answers. Let me walk you through again. The majority of what I have ever seen in past years, that students goofing here is misinterpreting what something means. So again, K, constant. That I don't think there's any room for misinterpretation there. Although I do see a fair number of people plug in 10 to the -9. It's 10 to the +9. Don't get your exponents goofed, or you cannot possibly get the answer right. Q, big Q is always a source charge. So I'm asking the voltage here because of this charge. If I want to talk about charge B, for instance, I am asking how much voltage does charge B cause at some point. So in this, I'll do B for you. The voltage due to B at the location of the test charge, I would use the charge of B. Well, my next number I would write is 7. Oh, come on. And then finally, R. The meaning of R is the distance from the source to wherever I care about. So I ask you this. What is that distance? What's the diagonal of that rectangle? What's the diagonal of a rectangle whose sides are 3 and 4? 5. Pythagorean theorem, anyone? A squared plus b squared equals c squared. That's it. That's it. That's it. Plug in and you get a number. Plug in, you get 12.6 times 10 to the 9, or let me make the smaller so I can fit it. That's not trig. Pythagoras. It's not. Ain't no sines and cosines there. Hey, what about the source test charge? Why didn't we use 2? -2. Why didn't I use the -2 coulombs feeling this? I'm not asking for anything about the test charge. Voltage only has to do with sources of electricity. Voltage doesn't depend on what feels it. That's a fact. Energy does, force does, but voltage is independent of that which feels the voltage. So you'll never use source charge. You'll never use the test charge when calculating voltage. Okay, and I'm going to go ahead and write down the other numbers. Oh, you see it? Does it see it? Clicky. Whoopsie. Negative. Ah, Dama, very important question here. And I haven't explained it at all yet. Go into that in a second once people are done, or closer to done. Because that gets a little deep. Take a second to reflect on this. Did I goof? Did I screw it? I screwed up. I got it 10 to the 10. Can't add. Wait. Oh, for God's sake. Nope, 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 nope. I cannot arithmetic either. Unless I'm greatly mistaken. Again. There we go. Yeah. My first answer is if you ignore the minus sign. I goofed. Okay. Has everyone had a chance to practice this for a minute? Dalma online asked a fantabulous question about what is negative voltage. We haven't dealt with negative voltage in circuits, but negative voltage is a very real meaning here. I want to reflect on what positive voltage means for a second. If I stick a positive test charge at a positive voltage, I have positive energy. I have positive potential energy. If I put two pluses next to each other, there is stored energy there. And if I release the test charge, woo, it zooms off into outer space. Right? The charges push on each other. There's a force, there's an acceleration, zoom off. Like charges repel, yeah? Okay, so if I've got a positive charge and a positive charge, that zooms off to outer space. What if there's stored energy that could be released into kinetic form? Well, where is my zero in this example? I have been harping from time to time on the fact that voltage is only as defined as it's zero. Where does V equal zero in this example? If I've got a source charge of 1, and if I round 9 billion to 1, I say voltage is 1 divided by R. When does that equal 0? When R is infinitely large, 1 over infinity goes to 0. I claim that I am intrinsically defining here, implicitly defining the voltage equals 0, our reference point, to be when charges are very far separated from each other. When I look very far from the charge, that's 0. Okay, so there's positive energy anytime two charges, a positive test charge, is anywhere near in a positive voltage field caused by a nearby positive charge. Well, what if I've got a negative source charge? There's still the ability for a nearby test charge, nearby positive test charge, to get energy, but which direction does it go? It goes towards the negative charge. Opposites attract, right? Okay. So if I want to get energy by going from potentially infinitely far away, where the voltage is 0, if I want to get energy coming closer, how do I go down from 0? As R gets smaller and smaller, as the particle is attracted, getting faster, I am gaining energy from the potential energy, getting closer and closer. Positive and negative attract each other, right? How do I go when I get closer and closer to get a smaller and smaller negative or a negative? Oh, I'm giving it away. You have a negative voltage. A negative source charge makes a negative voltage nearby it. That's what is logically required in order for potential energy to continue to go down below 0. Look, I've given an example of voltage is like height, right? Potential energy, mgh, is related to h. As I go up a mountain, I gain potential energy. As I go down the mountain, I lose potential energy. Remember that 1,000 times example? Well, a negative charge is like a hole in the ground. I have less than zero height. I can continue to lose potential energy by going into negative H's. If I get near a negative source charge, I continue to get energy from the potential energy by getting negative or a negative potential. It can give me positive or positive or kinetic. Or at the end of the day, plug in numbers and ignore it. No, we're going to do that later. The source charge is negative. Energy is going from the positive test charge to the negative. Energy decreases when a positive test gets closer to a negative test, to a negative source. Energy decreases below zero so that I can continue to release stored energy starting from zero. The closer I get, starting from zero, infinitely far away, I start from 0 volts, getting negative and negative. That's how you go down, getting closer. I'm decreasing energy. The negative charge is sucking the positive guy in. All right.
So if there's a negative charge, we'll have individually, you'll have a negative one.
Negative charges exude negative voltages nearby. Precisely.
So, what did you mean when you said there's a negative charge on beneath the building?
So the voltage, the potential energy of a negative charge, and it gives a negative value of voltage, gives a negative value of potential energy. Just like if I dig a hole into the ground, a sinkhole, a valley, below my reference height h equals 0, I can go into that hole. What's my height? I'm below ground level. I got negative height, negative MGH, negative potential energy. That's perfectly legal. Fantastic, deep, profound questions. We can come back to these. We will come back to these. I was originally planning to go into the why today. I do want to give one last chance for questions about this example or anything else on your mind here with voltage before we hit capacitors for the rest of the day. You good? You can plug in numbers and calculate, evaluate to your heart's content, give voltages, great. So let me review what we did yesterday class. Last time I took two formulas and I shoved them into each other and said, oh look, here's something actually useful. I took the capacitor equation, capacitor field equation, Q over A epsilon. We use Q over A epsilon. And I took the definition, the always true statement that voltage is electric field times distance moved through that electric field in the direction. And if I plug E in for E, I get capacitor voltage is QD over A epsilon. D is the distance between the plates. That's the distance the electric field is pointing, right? Electric field goes from pluses to minuses. And so if I go from one plate to the other, what distance have I gone from the diagram I drew before? D is the distance between. I had a student ask, very good question, what about the minus here? Where'd the minus go? The answer is, in a practical electronic circuit that I buy a capacitor for, I really don't care about the direction of the electric field. The capacitor is just a little molded piece of, not moldy, molded as in encapsulated device that I don't look inside. I don't need to care about the fact there's an electric field in there. I only care about what the charge does to voltage. So if I don't care about the direction of electric field, I just take the absolute value. Say the magnitude of voltage is the absolute value. And I'm not looking at which direction is it changing. So voltage across the capacitor is QD over A epsilon. And there are two very importantly different parts of this equation. Reflect on this. What does Q reflect? What kind of thing is it? Is it a distance? It's a charge. It's the charge on the capacitor. That's electricity. What about D and A? D and A are the size of the capacitor, how big, how far they are apart, how big the plates are. Right? Yeah? Those are physical properties of the size and shape of the capacitor. Those don't change if you change the electricity. You would have to physically expand or contract or do something physical with the capacitor with your hands, change it to make its capacitance different. Okay, so I just gave it away here. I'm going to define the ratio of the two electrical quantities, charge divided by voltage. I define that as the capacitance. This isn't always true equation. Capacitance defined as charge per voltage. I define capacitance as charge per volt. Notice, by the way, if I solve for V over A epsilon by dividing by Q, V divided by Q is not Q divided by V. Don't take this and get rid of the Q and think you've got capacitance. If I solve for capacitance here, well, let me do it here. If I solve for capacitance here, solve for the ratio of charge to voltage, I want to get these terms away from the Q and keep the Q upstairs. What I would do is multiply both sides by the reciprocal, and then I would divide both sides by the voltage. So I'm left with the charge to voltage ratio of A, over epsilon D. We're going to use this in a second. I might as well write it up here. Capacitance of a, that looks like cough. You guys remember epsilon naught? I'll give it to you now. Here's a homework question. Merry Christmas. I'm gonna do your homework for you. Well, as always, I'm gonna have you wrestle with it yourself first. Do you guys know what pico is? Pico is trillion. This is the practical value for electronics. Trillionths of a farad. Farads are huge. A farad is a huge amount of capacitance. 10 to the minus 12. Trillionth 12. Minus. I'm gonna give this a shot. Ready, set, go. All you gotta do is use the formula and plug in numbers. Do this. This should not be one of the hard parts of today's lesson. This is just plugging in. Centimeters. What are you guys talking about? What's our SI unit of distance here? You should always give your final answers in terms of meters, newtons, kilograms, seconds, square meters. How many square meters, y'all? Area is not measured in meters. Who's stuck? Lost? No? Okay. Um, let me give a hint. These are actually practical, possible. You can build this capacitor, although we don't usually build it as just two flat double plates. This is a realistic value capacitance, a realistic value of plate separation. Take the square root of this number and you get the length of the side. Try doing that. If your answer is bigger than the distance from here to the sun, or smaller than an atom, you goof. Check your powers. You should not have astronomically large squares or microscopically small squares. Okay, the correct answer is about 0.04 square meters. Question. Always meters in our class. At the beginning of every problem I ever give you, convert to SI units, and your answer will be in SI units. And never, you can answer with centimeters or millimeters or nano coulombs or whatever, but I strongly suggest you always start by going to the SI units and then recognizing, oh, well, let's see. If I've got, 0.2 meters, I can also say 20 centimeters. But that's your choice.
No, but my question was like, I forgot when you use something with a cube. So
What's the area? What's the area formula?
no, like area is always square, but I was like, if you like the volume, then you use volume, we use cube. Like say if you cube or we can do.
So what's the formula for volume? How many meters are being multiplied? So it's cubed. Look at the formula and pretend that your units are algebraic variables. Plug them in. That's how you can look at the formula. Okay, hey, follow up here. How big is this? What's the side length if I assume this is a square? Nope, nope, nope. This is F. You have to remember the formula for the area of a square. Solve that for side length. Okay, what's the formula for area of a square? Okay, how do I get rid of a square? When I plug in square root of 0.041, this is 0.2 meters-ish. How big is that? Oh, 20 centimeters, something like, oh, something like a foot by a foot. In practice, we don't use big honking rectangles like that in practice. And this is a practical, realistic sort of value. I have 360 picofarad capacitors at my house in my home laboratory. Well, that makes it sound fancier than it is, in my closet. And they're not huge sheets, 20 centimeters, but on the side, what we do is we stack lots of little sheets, alternating positive and negative sides with small separation between them. So you actually fit this something, 360 picofarad capacitor is smaller than my fist. And you can make many different variants of capacitance by changing the plate size. And also there's a thing called dielectric. If you put material in between the plates of the capacitor, you can get huge capacitances. Okay. I feel like this might be a point where I'd like you to turn to your neighbor and discuss real fast and give you 2 minutes, and then I'd like 2 questions from the audience about what we've done so far. Turn to your neighbor and discuss. What has Tucker done and why did he do it? Okay, that's 2 minutes, I think. Give me a question. Something here is not what it should be. No? You guys fine with this? For realsies? You promise? Jane, please. Okay. Okay, so now I would like to move on to using capacitors as a practical example, as a playground to encourage you to think about relationships, not romantic ones, but physics ones. Think about relationships between variables and about what you know about the core couple of equations. I'm going to ask you, suppose I take this capacitor and hook them up to a car battery. If I take this capacitor and subject it to 12 volts of voltage, what happens? How much charge flows onto the plate? Use the definition loop. There's only one formula that relates these quantities. Look at your notes, look at the board. Look around. Ah, Dalma, thank you so much. F is the base unit for capacitance. It stands for farad. Is a tribute to Michael Faraday, who discovered a butt ton of stuff about electricity in the 1800s. So F, farad, base unit. When you see an F there, I'm not talking about force. Okay, and if I solve the definition of capacitance, the defining equation that is always true, capacitance is charge per volt. If I just multiply both sides by V, I get Q equals C times V. I know C. I gave you C. 360 picos, 360 10 to the minus 12s, times what's V? What did I give you? 12. 12. Multiply these suckers out. Yes, Q and C. They are directly proportional, assuming the voltage remains constant. I mean, meditate upon this equation. Q equals C times V. If C doesn't change, V is proportional to Q. If V doesn't change, C is proportional to Q. I am seeing a lot of unhappy faces, and I'm not sure if there was just an OChem quiz or you guys are exhausted at this point of the semester. I don't blame you. I am too, if that is the case. Google question H. What's going on? How are you feeling? How can I make your life happier? You just want to sleep? My friend, I feel the same way. Give me some feedback. Ask me a question. Ask a question, give a suggestion for how I can make things clicky more. Yeah, please. Oh, I missed one on nodding.
Or times 10 to the negative 10. It's like
3.6, 10 to the negative 10, 360, 10 to the minus 12, mathematically identical. They're the same number. Yeah. I mean, 10 to the 2 versus 100, same number. You can use either one. Ah, here's one. Why does charge equals capacitance times voltage? Well, I take the defining equation for capacitance. C is defined as Q divided by V. And if I multiply both sides of this equation by V, well, V divided by V on the left just turns into Q, and on the left, right, I've got Q equals C times V. So I would say, why is Q equal to CV? Because I defined capacitance in that way. I'm hungry. We have an OChem midterm tour. I'm tired. I'm tired. I'm tired. Need self-medication. I mean, Can I explain where Q equals CV comes from? Yes. Well, hopefully what I just said made sense. Ready for spring break and tired. Okay, yeah. Okay, I'll take it. No big things that I feel I can. Here's another big one. Is Q given? No, I didn't give you Q. That's why I asked you for Q. Read the question here. How much charge? What's charge? Charge is Q. The symbol for charge is Q. I give you other variables, and these variables are related by an equation, so you can find Q. So you're not given Q. You're asked for Q. If you're asked for a variable, you're very often not given it. Although I do reserve the right to ask you, for instance, what is the voltage of a 12-volt battery on the final exam? They're all trick questions until you understand the physics. Until you understand anything, everything's a trick question. Then everything's easy once it clicks. Okay. Google question what? I want you to reason now about the quantities here. The physical example of what I'm thinking about is called a variable capacitor. The thing that's roughly the size of like this, on a variable capacitor. You can physically change the plate area facing each other by turning the knob. This is an old tuning knob. This is what you would turn to change channels in the olden days, in the classic days. So you can change A, and I ask you, suppose I take my capacitor, what was the area of 0.04 square meters? I'm gonna make that 0.02. I turn the knob so that it's now half the area. What would happen to the capacitance form, the value of C? What is the new value of C? The old value of C was 360. If I slice A in half, stare at the formula and tell me the new value of capacitance. Don't use your calculator for this one, for realsies. Free yourself from the tyranny of the calculator. First, can I really? Did I answer the question you asked, or was the answer that's what you're asking about and the dispersion dispute?
It's like I was not able to recall where do we use the units with Q, like raised to Q. So I start that. Yeah, but make you give it out.
Okay. Otherwise, that makes sense.
Yeah.
Okay, let's see what people think. Oh, hey, here's another thing for H, which is the person who started for question F for voltage. Yes. Okay, so I can call that time. I hope you didn't use your calculator. I want you not to always have to use your calculator for everything in your life. Here is how to avoid using your calculator. Look at yonder formula. Pull out where area is. We're asking how area affects capacitance. So I look at this and say that area is, well, A epsilon over D is the same thing as A times epsilon over D. I'm going to stare at this for a second. In this particular case, let's think, does epsilon ever change? No, it's constant in nature. Is the distance between the plates changing? No. Doesn't say anything about them being allowed to change. They don't. So these don't change. Whenever you're dealing with a ratio, a fraction, a proportion, constant multiples cancel out. I've just got multiplication and division. The ratio, in a ratio, these guys will be the same, they cancel out. So I can say that C is, what I say is C is proportional to A. I don't say C equals A, but I say C is directly proportional to A, which means that if A doubles, C doubles, if A triples, C triples, if A gets cut in by a factor of 10, C gets cut by a factor of 10. You can use the earlier method I taught you of bullshits and numbers to see this. Ignore these guys, trust me. Constant multiples and simple equations, they always cancel out. Let's say A is 5. C is 5, right? Now if I double A, what's C? Why does C change? C double. Don't get complacent, it gets harder than direct proportionality. But in this example, if I have half as much of A, then I must have half as much as C. Well, if I started with 360, I don't need a calculator to plug in numbers again. I can just say half of 360 is 180. Done. Okay. Now I ask you this. Here you must reason about the nature of charge, voltage, current, and blah. I've got the capacitor. Ignore this. I stated things slightly differently to the 3. I ask you this. The area of the capacitor plates, the effective area of the capacitor plates, the capacitance have both halved. I have an equation which relates capacitance to voltage, Q equals CV. I challenge you to think about the physics involved of electricity and tell me what happens when I turn the capacitor dial, what happens to the voltage on the capacitor. I will encourage you to think about the nature of batteries as well. Take a stab. Google question J. What do you predict new voltage on the capacitor is? I change the capacitance. The arrow means it's changeable. It's a variable capacitor.
Yeah.
Sorry. Oh, Kyle, question? Or talking to somebody else? Talking to somebody else. Okay, I got a lot of predictions and people are telling me that it doubles, it halves, and it stays the same. And it looks like roughly as many people are saying double, it stays the same, and the halving is. Okay, so here is how to reason about this. Q equals C, V equals Q divided by C. If I solve Q equals CV for V, I've got voltage as charge per capacitance. If capacitance gets half as great and voltage stays the same, then halving this up. Wait, but hold on a second. Why do I think the charge stays the same? What evidence do you have that charge stays the same? What I said before. Some don't change. You're not changing anything about the plate separation. Here, I don't know if charge is the same. So I have to consider I've got two component circuits. I've got really two unknowns, voltage and charge could both change. I must consider what he is attached to. What is the capacitor attached to? What did I say I do? I hook him up to a car battery. What's the entire point of a battery? What's the point of a battery? What does the battery do with charge and voltage and current and blah? A battery supplies whatever current is necessary to keep its voltage constant. Remember that question on the midterm? You change the resistance of a resistor, it changes the current. It doesn't change the voltage. Okay, so if the capacitor is hooked up to a battery, If I change the capacitance, I've got two unknowns, charge and voltage. I don't know which is changing. I have to consider everything I've been given. If there's a battery attached to it, the battery will supply some extra charge or reduce the charge on the capacitance. Charge on the capacitor. If I have capacitance, evidently charge must get half as great as well. Half over half is the same as before. Voltage is fixed. Correct answer for J is 12 volts. Does not change. The battery keeps at 12. Well, now, suppose instead of keeping attached to the battery, I'm going to cut the battery out. No battery. No battery for you. I've just got a capacitor, two metal plates sitting there. I just hold the capacitor up in empty space, free air. Then I turn its knob again. I ask you, do you know that voltage stays the same? That charge stays the same? If I change the capacitance, must.
No, no idea.
And which of these variables must change? This is K. Think about this. You've got a capacitor just sitting there. Yeah, now I'll remind you, Q equals C times V, or C equals Q over V, whatever. You can rearrange it however you like. What can change if I change capacitance? I have a relationship between charge, capacitance, and voltage. The whole point of the previous example is that if you know one letter changes, just by looking at the equation, you don't know whether V or Q or both change. You have to think about the physics. If I've got a capacitor just hanging out there, is it possible for its V to be affected? Is it possible for its charge to change? What is constant and what is variable? Make a prediction. Think about what you've learned about the nature of static electricity. Let's imagine the charge doubles. I used to have, what was it, 4 nanocoulombs? Now I have 8 nanocoulombs. Where did that come from? Did the charge all have babies? I removed it from the circuit. The capacitor is not connected to anything that can provide or remove charge. How did the charge get to the plates of the capacitor? What put them there? I didn't take a wand with cat fur rubbed on glass and add charges. I just turned the knob. I didn't add any electricity. Charge is constant. You got bare 2 pieces of metal with nothing touching them. You can't change the amount of charge on them. Not when they're not connected to nothing. Charge is constant. What does that tell us then? Q equals CV. If charge doesn't change, if capacitance gets half as great, what must happen now? What must happen now to voltage? If Q don't change and C gets half as great, what must happen to V? Tell me, Google question L. I just hold this out in free space. No battery attached. I make its capacitance 180 picofarads instead of 360 picofarads. I just told you that those 4 nanocoulombs of charge are stuck there. Or as my baby would say, they are guck there. What happens to the voltage if charge stays the same? Yes, it changes, but which way? Does it become 24? Does it become 6? Does it become 180,000? You can say much more than decrease, increase, change. Okay, so let's wrap this up. Put the pieces together. Step one, what I'm modeling here, what I'm showing you, you have to do every time is you have to think about the real world and what is actually physically happening before you can say this changes that, this doesn't change that. If you're just hanging out there, you got two pieces of metal not connecting to anything, charge cannot change. It disconnecting capacitor, the charge is just stuck there. So Q is the same. I am reasoning about how Q equals CV now and saying, well, if I know how this behaves, then I can say, how does this affect this? No, Delma, capacitors are not resistors. They're not resistors. There are connections between every component, series and parallel apply to, you could say the capacitors are in series, capacitors are in parallel, blah, 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 blah. But capacitors and resistors do not have the same properties. Okay, so reason about this principle. Q equals C times V. Q is fixed. If this number becomes half as big, what do I have to do to make this the product the same? For instance, suppose I have 4 times 6. What's 4 times 6? 24? 4 times 6 is 24. If I want to still get 24, I've got 2. If I have half as much here, what must happen to the 6? 2 times 1 is 24. And 2 times 12 is 24. What happened to be, if this number lost a factor of 2, and I multiply up to the same thing, this has to gain a factor of 2. The correct answer is, if I have the capacitance of an isolated capacitor, I must double the voltage. The voltage would become, in this case, 24 volts. We don't practice this. I really believe that this is one of the skill that I'm modeling here is one of the biggest things I can do for your brains that will actually be useful to you in the rest of your life in the real world. You're not going to be using these formulas, but you are going to be using the reasoning and the logic that we practice in. God willing. It's my goal. Okay. You now have everything you need for God willing. You now have everything that you need for this week. If there's something that you need that I've not given you, you're always encouraged to ask. We're done. I want to go back to Dalma's question real fast. Dalma, you asked, when you remove a resistor, current increased, but that's talking about comparing one circuit to a different circuit. Here I'm talking about an individual electronic component, a capacitor. What are its properties if I add or subtract or remove or do this or that to the individual component? If I change the capacitance of the capacitor, what is allowed to change and what is fixed? So you're thinking of saying, to remove the resistor increases current. You cannot just memorize decrease something, increases something else. You have to think about what it is. Okay, adios.